here we are, electron configuration, okay? All right, Sarah's like, she's enjoying this, okay? So now, we're going to talk a little bit about electron configuration. And what the book says, and I will quote, exceptional electron configuration. Now that means one of two things colloquially. Either it's exceptional as in excelente, or exceptional meaning it doesn't follow rules. Either way, they're wrong. It's not that excellent. And it does follow rules. See, the idea is that the atom is alive. It's dynamic. It's extremely organized. It fluctuates, but in an organized pattern. I can predict what an atom will do when it comes into contact with itself or another atom. Atoms are so organized that I can identify a material that's unknown to me based on the activity of the atoms it's made up of when in contact with itself or other atoms. There's no such thing as an exception in chemistry. It doesn't exist. There's an explanation for everything. Life is predominantly made of carbon. If it wasn't for something called hybridization, life as we know it would be non-existent. Hybridization is what the book would call an exception to electron configuration, but it's not an exception. Have I made myself clear? No such thing as exceptions in chemistry. They don't exist. Understood, Connor? Yep. Excellent. I'm very serious about this. I'm passionate about very little in life. My grandchildren, my children, the mole, and the fact that there's no exceptions in chemistry. Clear? Yes? Are you sure? Excellent. All right, let's talk about what this means. So we're talking about chromium and copper. Okay, I'm going to write it on the board, and we're going to do this. And by the time you finish it, you'll go, interesting point, Mr. Darcy. Excellent. Okay, chromium and copper. So if you have your periodic table, the one that's filled in, do the electron configurations for chromium and copper. Okay, chromium and copper. Okay, excuse me while I do this. Okay, you do it yourselves. Yes. No. You do it yourselves, and then we'll compare notes. Okay? Yes, Enzo.
You took my periodic table to photocopy?
I think there might be some over there. All right? Do you agree with what's on the board? Yes or no?
Yes.
Now, what the book is saying, although it's the same thing, we're going to be consistent with what the book is because that's what you're going to be reading. But what I write on the board and what the book says are slightly different. But what I want, the way I write it and the way the book writes, it's exactly the same. Okay, so in other words, they're doing this, they're putting 3D in front of 4S. That's fine. They're keeping the 3's together and the 2's together and the 4's together, okay? We can deal with that, yes? Yes? Okay, so that's what they're doing. So they're reversing these two. So they're saying this is going to be 3D4 and 4S2. Yes?
Yep.
And this one is 3D9, 4S2.
Can we keep it the other way then?
You can do whatever you like. It doesn't matter. Either way. I'm just showing what's on the book. I'm just showing what's in the book. Okay? Because they were reading in the book before we did this. So, all right? Now, this is the deal. If I look at, let's take one at a time. All right? Yes? If I look at this configuration in the 4S and the 3D, okay? It looks like this. The chromium looks like this. Yes? Is that the chromium? 4S2 and 3D4. You see that? Yes? Okay, now. And that's correct. Yes, that's correct. But that's not really what's true in nature. In nature, you get this kind of hybridized state. I'm going to use that word, hybridized. Is that okay? Because it's kind of like a combination. A horse and a donkey equals a mule. That's a hybridized, the mule is hybridized version of the horse and the donkey. Yes? All right. So these energy levels, even though I drew it the same, in the same level, they're not the same energy level. Do you understand that? That the 4S and the 3D are not at the same energy level. Is that clear?
Yes.
Do you understand that? That the 4S2 and the 3D4 are not necessarily at the same energy level. Yes? But what happens is this. And this makes perfect sense when you learn chemistry. And that is that a half-filled D is extremely stable. A half-filled P is extremely stable. A half-filled F, extremely stable. So you will see this kind of configuration with a P as well. Yes? This could be 6S2, and this could be 4F6, right? You're almost half, yes? Okay. But this is what it looks like, correct? Yes? What's the magnetic quantum number for this arrangement? What's the M quantum number for that electron? That's the last one that's in the filling. It's going to be, go ahead, plus
Plus 1/2.
No, that's the spin.
No.
The M quantum number. That's the spin.
No.
They have no memory of this.
+1.
Plus 1. Thank you. God bless Australia. Excellent place. Never been there. Is it nice?
Yes.
You like it?
Yeah.
It's home.
Yes.
You're a little biased.
Yeah.
That's okay. What we'll do is for the next video, I'll put on some Australian music. Okay? Like, what's your favorite Australian folk song? Walking Matilda? Or, was that Walking Matilda or something Matilda, right? I don't know. We'll look it up. He doesn't know. That's so weird. I know and he doesn't know. Okay. So anyway. So this is what happens. That almost half-filled D, remember, is very stable. Very stable. And a half-filled S versus a whole-filled S, not terribly different in energy levels. Yes? Half-filled, whole-filled. Whole, half. Half's a little bit higher energy than the whole-filled S. But they really are very similar in terms of energy structure. a half-filled S versus a completely filled S is not terribly different in terms of energy. But an almost filled D versus, an almost half-filled D versus a half-filled D, very different. So this is what happens, okay? It hybridizes, and it goes like this. This one here migrates to right here. You see that? So therefore, this is going to be 1s2, 2s2, 2p6, 3s2, 3p6. We're going to put 4s first because we like that anyway. 1 and then 3d5. So at first blush, it looks like an exception, but it really isn't. It's not an exception.
It's just another set of rules.
It's not another set of rules. Well, I suppose it's a set of rules, yes. Everything is a set of rules. Everything is a set of rules. But it's real. There's an explanation for it, a reasonable explanation that can be used all over the periodic table when you have almost a half-filled P or almost a half-filled D or almost a half-filled F, and you have that S electron floating around. 2 S electrons right there, yeah? So, you get it? Makes sense? Yes? Then the next one, you can predict what's going to happen. I'll put the D and the S here. This is going to be the D, and then this is the S. Now look at that. It's almost a completely filled D. That almost completely filled D is a siren singing that wrecks the Greek ships on the rocks. The song of the siren. Anybody read Greek mythology? Excellent. Enzo, well done. I'm impressed. What's the siren?
What about it?
What is a siren?
It's a kind of it's a creature.
It's what?
It's a creature. It's a mythical creature.
Mythical creature.
Has a beautiful singing voice.
Beautiful singing voice.
Attracts sailors.
Attracts sailors.
Distracts them.
Distracts them. They wreck their ship on the rocks. Yes. So this is a siren. We're not going to wreck our ship on the rocks, but it is that almost half filled. So what happens is this. This migrates. So it's filled. So this will turn into 3D. We'll put this, and then this will be 4S1 3D10. Okay? Now we'll study that in further on down the line when we talk about carbon hybridization. But you know what I'm going to do? I'm going to do that right now. It'll take a second and it'll be a connection that's going to be really cool. Okay? So, let's write carbon right here. Carbon is what? 1s2, 2s2, 2p, 2. Correct? Isn't that carbon? Yes? Okay. So, what does carbon look like in terms of its suborbitals? Its orbitals. You get an S. This is the valence shell. This is going to be the valence shell. What's going to happen? What do you think is going to happen? Based on our discussion, what's going to happen? Yes?
The second electron from S will go to that last circle.
Yes. We say the electron from the 2s orbital will migrate to the 2p orbital. Excellent. Mustafa, I'm telling you, excellent. He walked in with a haircut, I didn't recognize him. It's still hard to see the old Mustafa there. Have you had that short hair before?
Yeah.
Yes? Okay, good. Excellent. You should wear it more often. Okay? You're going to drive the women wild. Okay? You're going to drive the women wild. Okay? Dylan is throwing up in the back, but that's okay. Okay. All right, now, so this is going to look like this. Sorry, I already did that, right? Sorry, so this will migrate to here. So you get, over here you get what? 1 and 3. This type of hybridization, where this is all the same energy level,
No,
all same energy level,
no. They aren't the same. Because
Joseph is saying, he's saying no, like, that's going to change reality. I'm saying to you, when the S gives up the electron and it joins the P, S is down here,
He goes down to.
S is down here, and the P's are up here, right? You see that? So what happens is you get this hybridized level of this, like this. See that? Yes?
Yep.
This is called sp3. It's called sp3 hybridization. sp3. And when we talk about bonding, we'll talk about sp3 hybridization for carbon. How many people have heard of chemicals like natural gas? Natural gas is methane. Methane is CH4. I can form 4 bonds to the carbon. How can I form 4 bonds to carbon? How do I know that like that? I know that like that. I know that like that. You have done covalent bonding where covalent bonding is sharing of electrons, right? You knew that from biology last year, correct?
Yeah.
Well, look how many bonds I can put an electron there, 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 and there. 4 bonding sites. 4 bonding
And
sites.
if it was still on the S, it would only.
Exactly. If it was still here, then I'd only have 2 bonding sites.
Yeah.
See that? But this makes 4 bonding sites. You get it? Easy? We're done. Walking Matilda. What did I say before?
Walking Matilda.
Did I say walking Matilda?
yeah.
We'll have to look this up, okay? I'll be right back, and we're going to talk about electron, atomic emission spectra, and the quantum mechanical model. Sounds very exciting. Okay? Very exciting. Okay? It's like going out on a Friday night, you know, and talking about quantum chemistry. Exciting, isn't it? Okay? I know, like Mustafa's just so excited about this. Okay, talk to you later. Bye.